let me hear some sound and a really nice welcoming for Neal Ford. Ladies and gentlemen, come on to the stage. The stage is yours.
Thank you. All right, good afternoon, everyone. Today, I want to talk about granularity and communication in microservice architectures. My previous book that I wrote with Mark Richards was called The Fundamentals of Software Architecture, and the thing we were really trying to address there is, well, the fundamentals of software architecture. But we kept bumping into these problems that as we would dig into them, they got more and more complicated, and so we said, okay, too much for fundamentals books, so we set them aside. And we had this bigger and bigger pile of difficult problems in software architecture, and so when we finished that book, we looked at that pile and said, okay, what are we going to do with this? And so what we did with that was write the book, Software Architecture, The Hard Parts. But what it forced us to do is think about what is so difficult about distributed architectures and what aspects of distributed architectures like microservices cause so much difficulty. And it's a long book, it's 450 pages, so I'm going to give you the 45-minute overview of the key parts. And it really comes down to two kinds of coupling in software architecture: static versus dynamic coupling. Static coupling is how things are wired together, and that controls things like the granularity of microservices. How do you make that choice? I'll talk about that in a second. Once you've figured out how these things are wired together, communication is about, okay, now how do they talk to one another, and how do you resolve things like transactions versus choreography versus asynchronous and synchronous communication? So let's talk about those two aspects of distributed architectures, and we'll start with static coupling. And one of the key questions you have to answer if you build things like microservices is, what's the right granularity for a service in microservices? Because you've been told, well, it's single purpose. Okay, that's a great guideline, but are all messages a single thing, or is each type of message a single thing? Or is each category of type of message a single thing? I don't know, they're all single things. So what you need are some guidelines to help you iterate on the design of your services. And I can't stress this enough, how important iterative design is in architecture. I don't know any architect that's so smart that a perfect design just falls out of their head. But you can build a design and then iterate on it. But what you need are tools to allow you to do that iteration, and that's what I want to talk about now. What Mark and I have identified are two different forces in distributed architectures that we call disintegrators, which are things that encourage you to break things down into smaller pieces, but also integrators, which encourage you to bundle them back up into bigger pieces. There are 5 disintegrators and 3 integrators. Now, this is not meant to be a comprehensive list, because one of the problems we have in architecture is that there's no such thing as a generic architecture. Think about the architecture that you're working on right now. It's a combination of good things and bad things and stuff we like and stuff we hate and stuff we don't know where it really came from, but we still have to integrate to it, and all this mishmash of technologies and choices, and that's your software architecture. When you're a developer, you get really good at Googling for solutions to problems. I bet you know exactly what part of the stack trace to search for to get the best hits when you're looking for a problem. But when you think about your architecture, what are the chances that somebody else has exactly your architecture and all the combination of things and has the same problem you have in architecture and came up with a really nice, elegant solution to that problem and spent some time writing a blog entry about how to solve it so that you can go find it? That circle is getting really, really small. And so what you need to get good at is how to design your architecture. And so these are some starting tools that you can use, but you should be encouraged to identify your own disintegrators and integrators so that you build your toolbox. So let's talk about what these things are. The first of these is the most obvious one, and the one that everybody applies, which is service functionality. And this is an obvious boundary. You want to break things down around the idea of how they work. So if I have a notification service and I want to break that down further, the obvious place to break that down might be SMS versus email versus letter. That's breaking things down by functionality. But what happens very often is that if you only follow this guideline, you end up with a lot of very tiny little services. But then, to get them to do useful work, you have to wire them back together with workflows and transactions, and what you end up with is a very, very slow distributed architecture. Because you've broken things down too small, and now you're paying the penalty in communication and latency for communication. So, for example, customer service might cleanly break into profile and comments and preferences. So there's a clean delineation of many of these kinds of problems. But that's not the only one. The next one is code volatility. How volatile is code? So let's say that I have a notification service, and for text and email, code almost never changes. But because of weird regulatory requirements, code has to change quite often in the postal letter part of this world. And so that might encourage me to create something where code rarely changes versus code that always changes. So this is modeling your services around code volatility rather than purely a business function. Because it could be that there's a lot of shared behavior between text and email that you can take advantage of now without creating coupling points that you don't want. The third of these is called scalability and throughput, but this is really a placeholder for all of this family of operational, non-functional requirements. Performance, scalability, elasticity, reliability, availability. That very often determines how you want to break things apart. So for example, if I have a notification service and I have 220,000 texts a minute, 500 emails a minute, and 1 postal letter a minute, then the obvious breakdown of this is by how they scale and what kind of scalability requirements exist for each of these. This is, of course, one of the motivations for a lot of microservice architectures. Another one might be fault tolerance and that family and availability and reliability. Because if I have a single service like this and one part of it is volatile and fragile, then the whole thing is volatile and fragile. But if I break those up into individual services, I have more tools at my disposal. If one of these is down, then I might not route to it, or I can use circuit breakers and other patterns in DevOps to manage those kind of things, and so that gives me a little more flexibility. Now, you might think about, well, since these two are kind of non-volatile, or don't have fault tolerance problems, maybe I should just bundle those two together, but then what would you call it? Naming things is hard in software architecture, and I don't know what you'd call this thing, so you'd probably end up breaking it into 3 anyway. And there's my, don't know why that played again. So the last of these is security, and this is another obvious disintegrator in a lot of organizations where if I have one part that has critical information like private information or monetary information, then it's obvious that I might want to break those up so I can have better security constraints around part of my ecosystem. Now I want to stress that this is not meant to be a comprehensive list, but it's a good starter list of fairly generic things that are forces that encourage you to break things down. And too often, teams only break things down, but you also need to take into account integrators, things that encourage you to bundle things back together. And there are 3 of these. The first of these are transactions. One of the things you want to try to avoid in distributed architectures like microservices is exactly this scenario, where I have a profile service and a password service, and I need to register a new customer, and that means I need to update both the profile service and the password service transactionally, and this is considered generally a no-no in microservices. And in fact, if you want to model transactions, we'll talk about that in a second, when we talk about sagas in communication in distributed architectures. This is the problem that many teams run into when you break things down too small, is that now you need to actually get them to coordinate together from a workflow standpoint transactionally, and now you're doing distributed transactions, and nobody wants to do that. You want to try to avoid that as much as possible. And one easy way to avoid that is to bundle those back together into a single service. And now the transactional boundary is the service, not stretched out into your architecture. Now, the reason you might not be able to do this is because of one of the disintegrators that I talked about before. But now, hopefully, you can start seeing this idea of iterative design. You apply an integrator, but then you may apply some disintegrators and apply some more integrators until you get to probably not the best granularity, because that implies that everything is maximized and perfect. What you're shooting for in architecture almost always is not the best, rather that you're looking for the least worst. What's the least worst combination of trade-offs that will make this solution actually work? So database transactions is one of those very obvious integrators, but another one, data dependencies. This is another trap that teams fall into because they get really excited about the structure of architecture and the code, but then they forget that real-world systems almost always are connected to databases. If you are carefully observed that Mark Richards and I wrote the Fundamentals book, but we added 2 new co-authors to the software architecture, the hard parts, Pramod Sadalge and Zhamak Dehghani, because they're both experts on data, both operational and analytical data, because increasingly, data and data concerns are the concerns of architects. In fact, Mark and I worked on a lot of systems, distributed systems, way back 15 or 20 years ago with COM and Corba and a bunch of quaint old technologies like that. But in those distributed systems, we were mostly still relying on databases to manage transactionality. But when microservices come along, driven by this idea in domain-driven design of a bounded context, that means that the database is now part of your service boundary, which means that transactionality is now an architectural concern, and that complicates everything. But data dependencies also become an architectural concern. So let's say that I have this single service that's talking to these 6 tables, and I want to break it up into 3 separate services. Okay, well, I don't want all of these to talk to all of those tables. I don't want a single database, so I now need to do a distribution of the access for my data. It turns out that function A is writing to tables 1, 2, 4, and 6. Function B writes to table 3 and reads from number 5. And function C writes to table 5 but reads from table 3. Okay, well, this is just like the sliding match game little thing that you played when you were a kid. So let's move 1, 2, 4, and 6 over here to A, who needs those. We'll move 3 over here to service B, and we'll move 5 over to service C. And now we're all done. We can finish up and work on that. Oh, wait a minute. I've got lines left over. Well, that's probably not good. So I got to figure out what to do with those lines. Okay, well, I need read access between these 2, so I could just do that, but I don't really want to do that. In fact, I should not do that. This is violating one of those rules in microservices, because to do that, each of those services would have to know the implementation details, the schema inside the other ones, and that's what we're trying to avoid in microservices, is letting those kind of implementation details leak out. So that's probably not going to work. I could do this. Let them do inter-service communication. In fact, this is what you end up doing in a lot of cases in microservices rather than expose schema information, because this allows you to insert a contract so that if the implementation changes but the message doesn't need to change, you haven't broken anything, you stay decoupled. But what if this is really chatty and there's a lot of latency back and forth and this is soaking up a lot of your ecosystem? In many cases, it just makes sense to bundle those back together and make a bigger service boundary, because the data dependencies are too hard to untangle within your architecture. Now, you do hazard having the microservice police come by your organization and look at your architecture, and you might not get a gold star for having a perfect microservice architecture if you do this, but you'll spend a lot less sleepless nights trying to figure out why all this wiring is not working in your architecture if you do that. And the third of these is workflow and choreography. Turns out there's a pretty direct correlation to how complicated your workflow is and how much you need to coordinate that using something like an orchestrator or by bundling it back together. And this is one of the big problems in microservices, because let's say that I have one big service like this and I make a request for it, but I break it up into a bunch of different services. Now they need to talk with each other to fulfill this request. So if I make a request into this thing, then what if one of these is down? Well, now they're all down. Now, I've got circuit breakers and other stuff that I can apply here, but anytime you move into distributed architectures, you take this with you, the probability that things are not going to be available and that they're going to be slower, for example. What about responsiveness and performance? This is the thing that nabs a lot of teams in microservices, where in the single service, I can make a round trip in 1,500 milliseconds. But when I call in this constellation of services, now I've got to call from this one to that one, and this one to that one, and this one to that one, and return back to this one, and 3 times as long. This is the bad surprise that some teams get when they get their shiny new microservice architecture up and running. It's like, wow, it's really awesome, and it's really slow. So we got to do something about that. The other problem here is reliability and data consistency. If you're in a single process space, then you're pretty good on consistency because you've got a single transactional boundary. But here, what if one of these databases is down? Now, you can mitigate this with persistent message queues and a bunch of other fancy architecture stuff, but the point is you have to manage that yourself, and it makes your architecture more complicated. And in fact, in many cases, if that workflow is too complex, it's too coupled, there are too many calls, interdependencies between data, et cetera, maybe you're better off just integrating those things back together. So those are tools that you can use within your ecosystem to think about getting granularity right. And of course, this is the point that I was making before, that you get granularity right by iterating on design. It never comes out exactly right the first time. You have to iterate on this to see if you can hone in on a better design. So that's the static coupling side of the world in a very quick overview. Let's talk about dynamic coupling and communication in microservices. This is the most complicated part of our book for sure, and it took us a long time to figure this stuff out, because as we started looking at this giant pile of difficult problems, a lot of them came down to these communication problems about transactionality, and what we noticed was that we built all these sort of models, but every time you'd change something, everything would change. And we were trying to find a way, how do you isolate change in this world? Because it seems like it's highly coupled, that every time you change one thing, you have to reevaluate the whole space. And what we realized and finally identified are what we call these primal forces in dynamic coupling. And the first of these is communication. Is it synchronous or is it asynchronous communication? And this is a bit of a spectrum, because you can have different ways of implementing synchronous versus asynchronous. So this is the first of those primal forces. The second one is consistency. This is atomic or some flavor of eventual consistency. Now, you can't have ACID in distributed architectures because you can't get all 4 of the acronyms to work. In particular, isolation just doesn't work in a distributed architecture. But you can model atomic behavior by building an architecture that says, for this workflow, from the outside world, it either completes entirely or doesn't complete at all. In other words, there's never an intermediate state of during the state change. From the outside world, it either completely changes or doesn't at all. That's an atomic behavior for a workflow in a distributed architecture. And that's kind of a hard edge. And then there's this whole spectrum of eventual consistency about how eventual you allow that to be. The third force here is coordination. Are we using orchestration or are we using choreography? Because it turns out that really complex workflows benefit from orchestration because we identify two kinds of coupling in software architecture, what we call semantic coupling. That is the natural coupling of the workflow. So if you're ordering a book that involves a catalog and a user and an inventory and choosing a book and shipping the book to them, that is the semantic coupling of that workflow. The way you implement that in architecture is implementation coupling, and there's lots of different ways you can implement that semantic coupling, but the point is nothing you can do will make that less complex, but you can make it way more complex with implementation. So nothing in architecture is a magic silver bullet that makes the natural coupling of your problem domain less complicated, but you can accidentally make it more complicated. So there's a huge benefit from having an orchestrator for that workflow to handle that complexity for error handling and boundary conditions and things like that. What we finally realized, and our big insight in this book, is the reason that you can't change one of these without affecting the others is because you can't treat them a la carte. They're not single dimensions. These are all part of a conjoined three-dimensional space where communication is one dimension, consistency is the other dimension, and then coordination is the third dimension. And this really defines what we call dynamic quantum coupling in a software architecture. And what's interesting about this model is that when you think about a non-distributed architecture, what behavior does a non-distributed architecture have? Well, it's right here at the origin. It's mediated or orchestrated, synchronous, and atomic, which means that is basically collapsing all three dimensions away, and you get to the origin, which is no dimensions. And so once we realized this, we decided that, you know what we should do? We have three different binaries at either end of these spectrums, taken three different ways. That's 8 different possibilities. We just should model all 8 of them. And the assumption was some of these combinations will just be ridiculous and we can just throw them away as being improbably would never happen. But that didn't happen. It turns out all 8 of these are either legitimate patterns or anti-patterns in distributed architectures. So let's talk about all 8 of these things. These transactional workflows in microservices are traditionally called sagas, and this is named from Chris Richardson's Microservice Patterns book. That's not the origin of the term. It actually comes from distributed database days, but it's popular in the microservices world because of Chris Richardson's book. But he only identified 2 kinds of sagas, an orchestrated saga and a choreographed saga. But it turns out that's not the only force you have to think about, and so we modeled all 8 of them, and we gave them all sort of whimsical names of kinds of stories. And I'll talk about each one of these, what it means, and I'll show you the happy path and the error condition for them. For each of these, we basically have 3 sliders over here on the left that goes from atomic to eventual, synchronous to asynchronous, and orchestration to choreography. And we also summarize each one of them as along 4 different dimensions of interest. How coupled is this solution compared to the other ones? How complicated is it? Now, the complexity is multifaceted because there are 2 aspects of this. One is how complicated is it to understand, and the other is how complicated is it to implement. And there's one of these that has a difference between those 2. And then responsiveness or performance is the third one, and scalability is the 4th one. And the worst is 2 red stars, and the best is 2 green stars. So let's talk about what we call the epic saga. This is synchronous communication and using orchestrated, so we have an orchestration service here, but it also has atomic consistency. So what does that mean within a workflow? You see the dotted line around the outside? That's the transactional scope for this workflow. So while this workflow runs, we want the world outside this to view this as unchanged until the whole thing is changed. That's what we mean by an atomic workflow. So here's an example of the happy path through the epic saga. A request comes in the orchestrator, and it makes a synchronous call to one domain service, which updates itself, makes a synchronous call to another domain service to update itself, a synchronous call to a third domain service to update itself. Now everything is updated, and I can send a request back to my customer that says, yep, everything looks good. Notice these are all synchronous calls, and so this is taking a long time because there's a lot of waiting going on here, which is why responsiveness is not terrific in this architecture. But let's look at the error condition here. A request comes in, we make a synchronous call to update one domain service and update the other domain service, but when we try to update the third domain service, it fails for some reason. This is what's referred to as a compensating update approach to this, where now the orchestrator is going to go back to the two services that had already updated themselves and say, please undo what you did before, and then and only then can it return an error message to my caller. And the reason I have to wait until those compensating updates are done is because so many of you are familiar with the 8 fallacies of distributed computing, which was codified by Peter Deutsch back in the 1980s. Mark and I are gradually adding to that list. And the number 9 fallacy is that versioning is easy. And the number 10 fallacy is that compensating transactions always work. Because they don't. And if the compensating update doesn't work, you need to send a different kind of error message back saying, hey, now I'm in an inconsistent state and, really bad things are going to happen. So, but the atomic scope of this is forcing me to wait to make sure that all those things are resolved before I can go away. Notice that because of that atomic scope, that if during the course of this workflow, if a third service queries one of my domain services during this workflow, they're going to get back delta -1. They're not going to get the change. They're going to get what it was before. Until the entire workflow is finished, it still looks like it has that old value. That's what it means that the entire workflow is atomic. So we call this an epic saga because this is a long-running heroic story, a very long-running, as it turns out, because of all those synchronous calls. But this is a trap that a lot of early adopters of microservices fall into because this is the closest one to the origin. And this mimics what you're used to in a monolithic architecture, synchronous, atomic, and orchestrated. So this mimics a non-distributed transactional interaction, but it's very coupled. Trying to do that atomic scope is very, very difficult to achieve. And this is the one where the complexity is a single green dot because it's really easy to understand this. You don't have asynchronicity going around. You don't have complications with choreography. It's really easy to understand, but hard to implement correctly because of all the error states that you have to manage here. And this is often the very first attempt by a lot of teams at trying to build a kind of a distributed workflow like this. So let's take communication and flip the toggle from synchronous to asynchronous and create what we call the fantasy fiction saga. This one has the same topology that we saw before, but now we're using asynchronous messaging instead of synchronous messaging. So now a call can come in my orchestrator, and now I can send asynchronous messages out to all of these other services. Notice that in the epic saga, it's the sum of how long it takes all the requests to run, whereas this one is just as long as the longest running request. So this one is going to be many, many times faster than an epic saga because of the asynchronicity. But like many things in the asynchronous world, more complicated. Because in the error state here, I send out my request, and then one of them has an error state. It's going to send a request back, but the other two are still working on changes, and so now I've got to go back and tell them, nope, nope, undo what you just did, undo that. And then and only then can I send the request back to my client that says, I'm sorry, I could not fulfill this request. Again, that atomic scope is causing that delay in returning that. And so even though this is using asynchronously, it still doesn't have great scalability or responsiveness. We'll see how to get to those, make those scores better in just a second. This is, we called a complex story that's hard to believe in the end because of all of this asynchronicity going around. And if teams are not used to concurrency, this is going to be really difficult. But a lot of teams, this is their first stab at fixing an epic saga because they build the epic saga and it's like, wow, that's really slow. It's amazing how slow that is. And somebody says, well, I read on the internet that the way you speed things up is to go to asynchronous messaging instead of synchronous messaging. And it does. That will definitely improve responsiveness, but it's going to make it more complicated because now you've got deadlocks and race conditions and some other things that you have to deal with, and that may actually be worse than the performance problem. So this is very often a first attempt to fix that epic saga issue. So let's flip consistency over to eventual now and flip communication back over to synchronous. And what that does is reduce the scope of transactional coordination to the individual domain services and not the entire workflow. This is, by the way, what Chris Richardson called the orchestrated saga. So this is the one of the two that he showed. And here, in the happy path, we have a synchronous request that comes in from my orchestrator, making blocking calls to all of these domain services to get them to update stuff. And we'll update the third one and say everything looks good. But notice in the error case, synchronous call to the first domain service, synchronous call to the second domain service. Now, a synchronous call to the third domain service and an error state. Notice that now I can return an error right away and then go back and tell the others to update their state. Because I'm in an eventual consistency world, meaning that it's okay if these domain services are a little bit inconsistent for a period of time while I'm doing these compensating transaction updates and that sort of stuff. That's what it means to have an eventually consistent workflow versus an atomic workflow. And notice that a lot of these numbers have gone up to the better. The complexity is now way down. In fact, this is one of the least complex solutions because all the things that drive high complexity have been reduced here, and this one's easy to understand. You don't have asynchronicity, which is making it complicated to understand. It is still fairly coupled because of the orchestrator, and responsiveness has now bumped its way up out of red into a yellow, which is a lot better. Notice that in this world, if I make a call to one of these domain services while I'm in this error state, that call will get delta, not delta minus 1, because it's okay for these services to be out of sync in terms of the data on that workflow temporarily. So this is an easy story with a pleasant ending, really easy to understand, which is one of the reasons that this was the exemplar that Chris talked about in his book. Synchronous and orchestrator are the two easiest things to reason about, and you don't have that atomic coordination that's making things a lot more complicated. So if there is a default, and there's not a default, but if there was a default, this might be it, because this is good for most medium to complex workflows that don't require extreme scalability and elasticity. That extreme scale, that orchestrator is going to become a bottleneck at some point, and you might want to get rid of that, but then it makes your solution more complex. And as I said, this is, if anything, the default in a lot of those situations. So let's leave consistency where it is, but flip back over to asynchronous communication and create what we call a parallel saga. So here we have the same topology as before, but now we're doing things asynchronously, which means it's going to be a lot more responsive. But now we're in the land of race conditions and deadlocks and other sort of asynchronous beasts that you have to worry about in a distributed architecture like this. In my error state here, notice that this is much more responsive because now as soon as I get that error and it returns, I can return to my sender, and now in the background asynchronously fix up all the compensating transactions that I have to do to fix up the changes to get it back to a consistent state. And so now you'll see that we're starting to see green dots show up here in terms of these desirable characteristics. So a parallel saga, we call this multiple stories running at the same time. This is really attractive option for complex workflows at high scale. Complex workflows benefit from having an orchestrator to manage boundaries and errors, etc. But this one is more scalable because it's asynchronous, and that gives you better scale than synchronicity does for sure. So one of the things that you figure out when you start doing this kind of analysis is what drives coupling up and down within an architecture like this. And it turns out that synchronous, atomic, and orchestrated are the three main drivers for coupling, and two of the three of those are minimized in this case, which makes it one of the better ones. But concurrency is always a tricky thing in software architecture. So all the ones we've been looking at so far have been orchestrated. Let's flip the bottom switch over to choreography and look at the four choreographed versions of these architectures. And the first of these is atomic, synchronous, but with choreography. So I don't have an orchestrator now, which means that any kind of error handling or boundary condition information has to now appear in my domain services. And so, but we've moved atomic scope again. So in the happy path here, this architecture is very much a kind of a pipes and filters or event chaining kind of architecture where one thing changed to the next one, which changed to the next one, which returns some value. These are all synchronous calls, so you could either have the return come from the last domain service or go back through the request and response loop back up to the original caller. Here in the error condition, though, we have to go through and chain to one domain service, which can chain to another domain service. But then if I get an error state, I've got to follow that chain back up to get back to my original domain service to fix those things up to repair that error. Notice that these domain services have to have a lot more knowledge about the workflows they participate in. And if you have really complex workflows, then that means your domain services have to be a lot more complex to accommodate that. So phone tag is like the game of phone tag where you whisper in one person's ear and they whisper in the next ear and they whisper, and then after 20 people you hear what they say and whether it's believable or not. So this is basically the epic saga without orchestration. So it's more scalable than it adds more scalability to simple transactional workflows if the orchestrator is the problem there. But this is not common. The idea of choreography plus synchronous communication is not a common. This is probably the least common combination of these things. One of these has to be the worst one, right? So here it is. What we call the horror story saga. This is atomic consistency with asynchronous communication and choreography. This is the most complicated thing you can do because all the tools you have to handle complexity have gone away, but all the complexity is still there. So this is very much a kind of a chain of events pattern, but you can do it asynchronously. So this could be either request response or broadcast messages that happen in this architecture. So either one of those are possible. So the other possibility here is something like this, where you're doing broadcasts and then getting responses back. Both of these are legitimate versions of the horror story saga. But here's the problem. When a request comes in here and we get into an error state, notice that we don't have an orchestrator to manage the compensating updates. So the service has got to figure out how to do that. But while I'm in this error state, imagine if another request comes in, and then another one, and then another one. I've got to start keeping track of what my pending transactional states are, and then another request comes in that's based on the outcome of one of the earlier ones, and then my head explodes. The number of error states is just too incredibly large in this world with no tools to really handle those things. So this is very much an anti-pattern. And it's a well-intentioned but flawed attempt to achieve high performance with atomicity. And literally within a month of Mark and I coming up with this taxonomy of communication patterns, the project I was working on, the architects on that project brought me a design that was a horror story. And here's exactly how they got there. We need super high scale, which means we want asynchronous and choreography, but the business says it has to be transactional. Congratulations, you've managed to find a horror story. We ended up implementing something different to fix that. So there's just two more of these left, and they are fairly simple. If you go back to eventual consistency here in synchronous, you get to the time travel saga. This is basically just a choreographed synchronous workflow from one to the other. This works well for a chain of responsibility kind of projects or electronic data interchange kind of things, for example. The error state here is managed, of course, through the individual services because we don't have an orchestrator here to manage that, so that drives complexity up a little bit, but this is almost always in a particular shape, and so you choose this because you're choosing this kind of event chaining or a chain of responsibility kind of pattern. So time travel is one that moves atomically through time. Like I said, this is best for pipeline kind of problems, but difficult to build complex workflows because you don't have things like an orchestrator. And the last of these is the anthology saga, which is choreography, but using asynchronous messaging. And so this is much faster, of course, because we're not making as many synchronous calls. And we can do the same kind of broadcast versus event chaining kind of patterns here as well. This one is also very attractive for super high scalability. Notice all the green dots over here for scale and the performance. So this is a loosely associated group of short stories, the opposite of the epic saga, the least couple versus the most couple, and it's best for these kind of pipes and filters kinds of ecosystems. So one last observation about all this. The benefit of doing this kind of holistic analysis of a problem space like this is that you learn what forces drive things one place versus the other. And so one of the things you constantly hear is that, oh, you shouldn't use orchestrators because they drive bad behavior. And sure enough, if you look at this one, that's not terrific. But you look over here, it's orchestrated as well and much better. It turns out the thing that's driving that bad behavior is the combination of orchestration plus atomic synchronization. So there are three coupling drivers that you figure out by doing this. As I mentioned, there's a strong correlation between complexity of workflow and usefulness of orchestrators. Choreography works best if you have less complex problems. And be careful about fixing architecture characteristics by trying to change just one dimension, because you have to think about all of these things as a three-dimensional conjoined space. Thanks very much for having me. I hope you enjoyed it. I hope it was useful. Thanks.
Make another big applause for Neal, please.
Thanks.
It's awesome. So, Neal, if we agree that we have a couple of questions, I wonder if you can help me with the first one. How common is that using monolithic first, then using microservice architecture and back to monolith due to less complexity?
It happens a fair amount because you end up breaking things down too small and then you end up bundling them back together. So Simon Brown has a great quote that if you can't build a proper monolith, what makes you think microservices is the answer to your problem? So very often teams learn that, and good modularity, you have to have it in monoliths and microservices. So microservices is not a magic solution.
Great. Cool. The next one. Why is team organization not a reason for services?
So
service
that's a
operation,
great,
I believe.
That's a great question. This goes exactly to what I said before, that it's not always, but within your organization it may be. You have to find your own disintegrators and integrators. We're just giving you a generic list, and our list is not comprehensive, and so team structure may very well be a driver for how you end up with your granularity because of Conway's law. So it absolutely could be a reason within your organization. My list is not comprehensive.
Great. Okay, maybe we have maybe only one. If we have a monolithic if we have a monolithic which use some microservices, then can we say we have a microservice infrastructure? Like we just have a bigger microservice and some small?
Hey, if you have a pet cat, you can say you've got a microservice architecture if you want. I mean, nobody's going to grade you on that and come and validate whether you have a microservice architecture or not. I mean, the question is, so you have to understand the philosophy of microservices. Are we building a highly decoupled distributed architecture with good separation between the parts? If that's true, then you're building a microservice architecture because that's the definition of a microservice architecture, not some particular level of granularity or number of lines of code. It's the philosophy of separating things, having highly decoupled, bounded contexts that communicate with each other in a highly decoupled way.
Awesome. Neal, in name of all the craft organizer, I want to give you, thank you, Neal, for your wonderful talk at Craft.
Thank you very much.
So please help another applause
Thanks.
for our rockstar
Thanks,
today.
everyone.